fact, I should have written the unitarity equation like this. And T dagger minus T. Okay, so we were doing an example at tree level, already to see what tree level unitarity is like. And so I chose this S matrix element where two particles fuse into one new particle. And it's a slight cheat. So we'll do a better example, which is not cheating, in a minute. But it's a slight cheat because, of course, if these two particles could fuse into this, then this could not possibly be a stable particle. It could actually decay back. So then, rightfully, I should not talk about an S matrix element for two particles and an out state, which is actually unstable. But this is at such a low order that it doesn't even know that it's unstable. So let's do this tree level example just to get the basic idea, but with that slight mistake. And then we'll do an honest example. Okay? And I'm also going to add to it another process at tree level, which is this 2-to-2 scattering, which is an honest S matrix element. All these are stable particles, or electron, or fermion, or whatever. And so at the level of formulas, IT is, okay, it's all amputated, it's just the S matrix element, if you like, so it's this, that. And here it's just this internal propagator, where P is just the sum of these external guys. Okay. So really I should multiply here by 2 pi to the 4th to be pedantic. So if I really wanted to write it like a robot, it's K1, K2, and if I call this P, then it's K minus P, where K is just defined as K1 plus K2. This as short as possible. Here, I should multiply by 2 pi. So this is just the overall. If I wanted the matrix element M, then I would drop this overall delta function of energy momentum conservation. But at the level of T, we would write it, and it would be, so this would be, I guess let me use the same notation, but this is K1, so these fermionic things. So maybe I should, this is K1, this is K2, this is K1 prime, this is K2 prime. Okay, and this is K minus K prime. The overall momentum conservation, where just to keep it brief, this is this, and this is this. Okay, so I guess I should have just called this K. Okay, so now let's test this equation, okay, which is the master equation. It has to be true by unitarity, but let's just see how it works diagrammatically. So let's calculate T minus T dagger over I. But which matrix element should I calculate? And so I'm going to calculate this tube psi to tube psi. And I think this came up in the homework. When I say this, of course, I mean psi plus psi bar. I mean particle and antiparticle annihilation. Okay, but I sometimes just say this, and but if you want here, let me say it from psi plus psi bar. So my matrix element is between this two-particle state, particle-antiparticle state, and then this other particle-antiparticle state, where this is momentum k and this is momentum k prime. Now, what is this? So we're looking at this term here. So we're doing this all at tree level. Okay. And let's see if I should. So this is the matrix element that I want to use. I don't want to consider, so here, maybe I should just do it like this. No. So let me, so there are cross diagrams. I'm doing two fermions, two identical fermions. Fermion, antifermion, to the same fermion, antifermion with different momenta. So in principle there are cross diagrams that you know to write down. We'll see why I'm focusing on this guy in a second. So let me ignore all these cross diagrams. Then, when I'm doing this, I'm basically taking the imaginary part up to a factor of 2 of t, and that's this guy here. So let's do that. There's a so the I here cancels the I there. So I'm really taking it before without the I. So the only imaginary thing is the I epsilon, where we use this standard formula. Okay, the imaginary, I'm just using the identity, imaginary part of 1 over x plus I epsilon is minus pi delta x. Okay.
Quick question.
Yeah.
On the second line, you're adding the amplitude for 2 different processes, like a 2 to 1, and a 2 to 2?
Yeah. What do I mean? I mean that these are. So maybe I should put a comma here.
Yeah.
If I'm listing all the matrix elements of ID, you imagine it's a huge matrix, and I'm trying to write down all the different matrix elements, then this is one of them, and it sits in the 2 fermion, 1 boson matrix element. And then there is another one, which is at the 2 fermion, antifermion matrix element. Looks like this, and of course, you know, it's as if I'm listing this all the matrix elements of this huge matrix. But I'm just telling you to zoom in on the same thing here if you want. All of these are contributions to this matrix. So if this is confusing, then you should ask me, but right now, because this is just the S matrix. This is what we mean by S matrix in the sense that there are really indices here. So if I wanted the K1 and 2 P matrix element, it would look like this. If I wanted the K1, K2 prime, purely fermionic matrix element, that looks like this, etc. So I won't invent a beautiful notation beyond that unless you specifically request one. So if you've never seen this identity, you can prove it. Either you can do some examples with contour integrals, or even easier, you can just calculate. You can make the denominator real, figure out what this is as a function. You'll see it's a kind of Lorentzian, and it's getting more and more peaked as a Lorentzian as epsilon goes to 0, and that the area under the curve is minus pi. So however you would like, you can just check this identity, in which case applied to this thing here, I get a delta function, which puts you on shell. So taking the imaginary part is really taking this propagator on shell here. And then I have 2 pi to the 4th. Okay. So let me see. And so these minuses, of course, cancel. Okay. So that's one side of this equation. Now let's look at T dagger T, the other thing I'm supposed to compute, with the same, but looking at the same matrix element, which is psi bar psi, this is k and k prime, and this is equal to, well, this is actually matrix multiplication. So I have to sum over a middle index. Okay, so first I have to do T psi bar psi is the first index, and then there has to be a second index, which I'm summing over. So that is, so at tree level, it's just this boson that the two fermions could turn into. And so that's what this is. So this is K and K prime. And if you want, let me give this a name, P. Okay? And so what I'm supposed to sum over, formally, we're supposed to think of this as matrix multiplication. So matrix multiplication, you pour rows into columns, right? So I'm supposed to take the last index of the, I'm supposed to take the last index of the first matrix and put it in, and multiply this index, multiply this matrix element by this other matrix element, okay? And sum over the repeated index, right? So this is matrix multiplication. So let's attempt to do that. And this is equal to, so our relativistic sum, summing over this one boson with all possible momenta, P, okay, is this. This is our friend, the relativistically invariant sum. Okay? And then I have to write each of these separately. And for that, I have handily kept the formula there, right? So that is the minus IG and the complex conjugate IG, that's going to cancel. And then I just have these two delta functions sitting around. So 2 pi to the 8th, and then delta 4. Okay. And so, as I've shown you before, this can be written as a full 4-dimensional integral with a on-shell constraint. On-shell and positive energy constraint. So this is exactly this, right? And then we have the G squared divided by 8. Okay. So we can just do the P integral, and we get G squared, and sorry, I wanted to be a little careful. This had 2 pi cubed. That slash there meant 2 pi cubed. So it's not quite, so that's the same as, whereas this slash means 2 pi to the 4th. So I need an extra 2 pi. Okay. So then I get 2 pi to the 5th, and then delta k squared minus m squared, and I get a net 1 delta function because this. Okay, and oh, sorry, when I did this, I took the imaginary part. Actually, this is twice the imaginary part, so. So, fortuitously, they're on the same line. These are, in fact, equal. So we have verified this thing. Of course, it had to be true, but we just wanted to see how did the diagram do it. And you see, the way it worked is that the higher order diagram, the imaginary part in this matrixy sense of the word, it's not really imaginary part in general, because this is actually a matrix. But this anti-Hermitian part is the way to say it. The anti-Hermitian part of this T ends up being something related to the square, this matrix sense, of lower order diagrams, or lower order S matrix elements squared are giving the higher order anti-Hermitian part of T. Okay? And that's what we've just checked. Here is something at low order, it's order G. Here is something at order G squared. So something at order G squared is reproducing for us the imaginary part, or if you want, the anti-Hermitian part of this order G squared effect. Okay, so that's what we checked. You can check yourself that if in fact I have my k and k prime such that this thing is, so for a generic k and k prime which are close to this being on shell, namely where this would even make any difference, or either side would be non-zero, that the cross diagrams that I neglected in this little discussion, because it would take too long to write it out, the cross diagrams would not contribute. Okay, so if this guy is actually close to being where this matters, then you should check for yourself that the cross diagram, which for example would have the intermediate line being, say, k2 plus k1 prime. Just because k1 and k2 add up to almost on shell, in general, k2 and k1 prime would not. Okay. But you can, so I'm being a little sloppy about the cross diagrams, but if you would like, replay the whole thing for yourself with the cross diagram thrown in, and just keep checking that, in fact, the entire unitarity equation is satisfied. Yeah.
The matrix element honestly includes the cross diagram, right?
Yes, as long as it's the same files as, yeah. For example, if I had made it 2 electrons to 2 muons, then I would have, so introduced a flavor like that, then I wouldn't have had a cross diagram.
Right.
But I didn't want to get into that. I'd rather you just write out all the cross diagrams and just check that this thing continues to go through. So, similarly, when you include so this was, of course, a check. It's checking. What we'd be doing is just check of this. This is the master equation. So this thing is either called, you can call it the unitarity equation, of the S matrix, the non-trivial part being the T matrix, or you can call it a generalized optical theorem. to the next easiest example. But again, this one really kind of captures the essence of this equation better than just this purely tree-level process. As I said, the tree-level process includes a small lie, which is we're treating this as if it was an honest S-matrix outstate, and yet the fact that this could produce this on shell means that this could decay back to this, which means it's not stable, and I should not have treated it as an S-matrix. But nevertheless, let's do a different example. That's example 1. Checks. And so 2 is very closely related to the thing that we just studied. Okay, so self-energy. So it's this process, and here, just for class, here it's tree level, and so the cross diagram irritation, I think it's fair game to say it's your problem, not mine. Here, we're about to do something loopy, so things are hard enough. Let me try and kill the cross diagrams for simplicity by saying that I'm looking at, call this the electron psi. And let's just say there are 2 species of fermions. And I'll use this notation for the second species. Let's call it the muon cup or something. Okay? And this is our friend phi again. But now it's not, I'm never going to write it as the outstate. It's just an intermediate part of going from electrons to muons. Okay? And then I'm going to write another one. So this is a contribution to the T matrix element where you have electron, positron going to muon, anti-muon. Okay? Electron, positron going to muon, anti-muon. But there's another thing you could have. You can, of course, have electron going to itself. One of the things we just studied. But you could also have a higher order contribution to this process. Now that I really mean the process. Okay. Because I'm going to draw this. This is an interesting process. Because virtually, you're going into muons, a muon loop, and then going back to electrons. So this and this actually do add in amplitudes. You see, they're both contributions to this S matrix element. Okay, so let's look at T electron, positron goes to, as a matrix element, electron, positron. And I'm again taking this anti-permission part. So okay. So let me do it for so I'm going to do it. So I'm going to do it for K1 plus K2 and K squared not near okay. I'm nowhere near. I'm not going to be anywhere near this guy being on shell. Since I'm not near it, whether I use the tree level approximation m squared or the loop corrected m squared physical, it doesn't matter. I'm not near any of these things. So this particle is not on shell. Okay? So then, this idea, so when you read this picture, we're used to resumming these bubbles and putting the self-energy in the denominator. Now it doesn't matter. That was because perturbation theory was breaking down when this guy is nearly on shell. Okay? For this example, I'm not going to be anywhere near on shell. So therefore, don't need to resum. In other words, this diagram is really just I over k squared minus m squared plus I epsilon times this thing, this diagram, times, okay, just for emphasis. That's it. Why? Should I keep the second loop? No, it's small. I mean, I'm doing perturbation theory here. And there's nothing killing perturbation theory like, so this is easier. Again, I'm trying to do the easiest things here. This is easier than the full self-energy discussion that we had before. Because there, I said, let's study it when this scalar is nearly on shell. And now, I'm just saying it's far off shell, but this is just a higher order correction. Okay? Let's see what difference it makes. So I'm doing that for convenience. So I can just focus on the new thing. Well, that means that what we just studied over here is irrelevant. In other words, here we had exactly the same as the first diagram. Sorry, not the first, the second of the three diagrams you see there is this diagram here. And indeed, it had an imaginary part. There it is. But it had an imaginary part only when k squared was on shell, or at least near on shell, so the distribution makes sense. I'm far from that. So you can drop. You don't have to worry about this. In other words, in calculating this, we can drop this part that we just worked hard on over here. Since the delta k squared minus little m squared equals 0. So if I don't have to drop it, I can keep it, but it's 0 in the regime that I'm studying. Okay, so that allows me to focus on only the new thing. And so here it is. It is minus 2. So let's see. So there is the IG here and the IG here, the minus IGs here. They're going to come in squared. Put something squared. Then there's going to be this propagator. So that's I over k squared minus m squared plus I epsilon. And as I said, I don't need this I epsilon because I'm far off shell. Okay, so I'm not going to write it. And in particular, when I'm taking this imaginary part that I'm doing here, I don't need to focus very hard on this thing because it's just not there. This thing is all nice and healthy and non-zero, and so this is not coming in. And all of these i's are squaring away. So in terms of taking imaginary parts, that is, there's going to be a cancellation between this and this as far as all these factors are concerned. So instead, who is getting imagined? It's this blob here. Okay, everything else, all of these factors are squaring with these guys so that it's real. That's not what's going to give a non-zero contribution here. It's only because of this blob in the middle. Okay, and that has a name. It's the imaginary part of sigma, and for people who are being careful or watching me, try to be careful. Remember that the sigma was, so that blob, So I just remind you of something that I've defined. That sigma is defined actually like this. Okay? Just so it looks like something like mass self-energy. Okay? But that means, that's how we define that notation. But now we are using it perturbatively in sigma because I'm nowhere near on shell. Okay? If I'm nowhere near on shell, this thing is exactly, this is like I k squared minus m squared plus I epsilon. And that was just the first term here. And then, now you can see what will happen. There will be a plus I sigma over k squared minus m squared plus I epsilon squared, right? That's the second term of this geometric series. And, but if I want to write this as the square of the propagator, in other words, there's a propagator and there's a propagator, well, there's two powers of I there. So that would be putting an I squared there, but then I'd have to put a minus I, okay? So that means that it's minus I sigma that remains in this T, okay? It's just a minus I sigma. And, that the IT has a minus I sigma. All these factors that you're looking at, fine. And this thing is secretly a minus I sigma. Okay, that's all you can work this out yourself, but I'm telling you. You might say, where did that minus I come from? It comes from this funny definition of sigma. That it's not literally the loop. Because you want to call it the propagator squared times something. And that's minus I sigma. Okay? Because we're going to take this out. We've already accounted for it. I wrote it there. So it's not this. Now, the I and that I go away. Okay? So when you're doing this, you're really taking an imaginary part. Again, you're taking kind of twice the imaginary part, and that's this T2. And there's a minus sign as well, and that's the minus. And then it really is imaginary sigma. Okay, so there. Now I've accounted for everything. You can check it. And you may recall that we worked this out while we were understanding decay rates and all of that. And the answer was that this is a half of this. So I did it with just one species of fermion before, but it's the species that's in the loop. Okay. And so we get the halves cancel. So this result is equal to this times this is K1 and K2, this is the K1 prime and K2 prime. So you can lend one of these factors and these propagators and glue it back to look like this, okay? And this is equal to T dagger E bar to mu bar T mu bar E bar, where I'm summing over my mu bar it's matrix multiplication, but where the index that's being repeated in sum is in fact a 2 fermion intermediate state. Okay? And you might say, I don't see where the summing is going on. Well, that's because this thing itself was the inclusive thing. So this thing, when I wrote this diagrammatically, what I meant was that this is K1 and K2, that secretly here, with 2 omega K, 2 omega K prime. Okay. And momentum conservation, of course. So I call, so this is K minus K prime. So this is K momentum coming through. And, sorry, I should have said K1 and K2. K1, K2, K1, K2, and putting primes on it. No, I should have given it some other name. Damn it. K double prime. Take that. Okay. So this intermediate pair, all I'm saying is that call this K double prime, 1 and 2, has to add up to K 1 and 2, obviously, by momentum conservation. But if you, again, you have to go back in your notes to see when I calculated this imaginary part, and that it came with these integrals. Okay, when I draw this notation like this, I was actually summing over the final state. Okay. Because, and remember, we were doing this in the context of a decay rate for this guy. So, of course, the rate included all possible final states that you could decay into. That's what this thing is. So this summing that I'm doing here, in this context, we see that it is precisely this, right? This thing here is precisely enforcing this part of the thing. So we're verifying that, again, this grand equation, which is a million equations in one, okay? We're verifying that it is true for this case. Now, in fact, it's such a grand equation. There are things that obviously are left out. For example, at the same order as this, I should have had this, plus all the cross diagrams, where it's the electron in the loop, and so on. And indeed, I should have. And in fact, we could have written all of that out. But if you like, one way of saying what I'm focusing on. You see, there's such an infinite number of equations simultaneously written here that I can only sort of zoom in and focus on some aspect. But just to crystallize which aspect I'm looking at how, say, the muon, or say the muon mass, contributes to this equation, which starts with purely electrons in it. So we're seeing certainly here how the muon contributes to this on this side of the equation. We're seeing how the muon contributes rather explicitly to this as a literal final state of these two T's on this side of the equation, and we're seeing there's a match. Okay. Indeed, if I had the steam to do this, one second. If I had the steam to do this, we would see that contribution play out here as well. Okay, it's just I'd have to deal with all the cross diagrams, which I don't want to do. But that's the loop level thing. And of course,
I was just going to say this loop term with the electron self-correction would end up becoming the matrix product of the electron scattering.
Sorry, you're saying this thing.
Yeah.
When I plug it in on this side and work out what it is, I would find that it was equal to the thing like this. Okay.
Yeah.
But it would be the lower order one. In other words, it would look like.
Yeah.
Okay? sort of weird crossed versions. For example, there is a diagram, I shouldn't even say crossed, here's another one. I should just say dot dot dot, but just as an example of how hairy it can be. That's not crossed in any way, that's just a completely different diagram. And that diagram has as many G's as that diagram, and so it's just as important. And so you would get, certainly you would get this effect from that, but you'd also get other weird things, like you could have so it's interesting, but so there are many, you never run out of examples. Play around yourself and see all the different things you can do. Okay, so just so this is how the unitarity equation plays out blow by blow. There is a interesting feature here, which you're seeing happen, which is this equation doesn't make sense. Or rather, this equation cannot be read for a fixed order in perturbation theory. If I just want to look at the 10th order in perturbation theory, well, I'm just looking at terms in T of 10th order. Well, on this side, if I'm looking at those terms, it's, you know, if this is 10th order, then this could be first order. So maybe the right way to say it is, this equation clearly connects different orders in perturbation theory. That's the right way to say it. Now, why? Because we have T minus T dagger over I, and we have T dagger T. And so if I take T, if I work on this side to say 10th order G to the 10th, what's that? Then here I'd have to keep order G to the 0 times order, sorry, no. So it's order G to the 0, there is no T, because T is the deviation from doing nothing. So that's why T is nice, okay? So you have to start at, say, at least first order, in which case you can only afford order G to the 9th here. Or you could have order G squared times order G to the 8th. Or you could have order G to the 9th here, order G here, okay? So but the interesting thing is that if you work to some order here, only lower orders show up here, okay? Which means that if you already have calculated T to lower order, to some order, you get some free information, okay? So that means that low order perturbation theory implies a higher order free result. By just multiplying and adding these things in some way, I am able to recycle them into a higher order result. Now, unfortunately, there's a catch. I would like to get the higher order result for this, because that's the ultimate thing everybody wants to calculate. Instead, I only get a piece of the answer. If you like, it's like getting the anti-Hermitian part of the answer, whereas I would like the entire answer. So it's like somebody told me half the information I'd like at higher order. Now, I could just go and calculate the loops at higher order and do it that way. But what it's saying is that the lower order calculations contain within them already a lot of the information about what's to come in higher order, okay? That unitarity is a relationship between different orders in perturbation theory in a non-trivial way. This is unlike, for example, Lorentz invariance. Lorentz invariance will connect diagrams at order g to the 10th with some Lorentz transform diagrams at order g to the 10th. It does not mix different orders in perturbation. This does. Okay, so it's something different, it's something novel, and it turns out to be incredibly valuable. Okay, there are ways in which using this trick allows you to calculate a lot of what you want at higher orders for less effort. Okay, notice it's not obvious that it's less effort. For example, this is not really multiplication. It's matrix multiplication, and it's matrix multiplication in a Hilbert space, which is infinite dimensional. And so you see that in the end you end up doing integrals, like summing over repeated indices. Oh, it's just doing 6 multiple integrals. So it's not like it's that easy. We're already doing multiple integrals just to calculate correctly. Nevertheless, it is still true that under certain circumstances, this is a very powerful insight and allows you to make money, okay? Or not, to be happy. What else do I want to say about this? There is a sense, and I ended up taking up a half a lecture last time I taught this to say it, because I said it wrong. So let me say it right, and then just assert it and say, you know, I'm not going to talk about it any further, which is that this equation it gives you a lot about iterating from lower orders and getting higher order results, but there's this sort of restriction to just getting the anti-Hermitian part of the higher order answer. But in some sense, if you throw in the extra assumption, which I think is axiomatic, that of causality, which is that the causes precede the effects, not just relativistically, but even just in a non-relativistic sense. Quantum mechanics. We know this, right? We're doing quantum mechanics, so we start with the initial wave function and you evolve to the final wave function. But if you put in that fact that you know that that's there, it's not immediately obvious in these diagrams that you have a Hamiltonian that's giving you all these formulas. But if you just add that extra fact to the story, then these things actually, with that information, allow you to calculate the entire higher order correction. Okay? In other words, the higher order corrections are not this sort of independently new things that you're being forced to calculate. They are there for one and only one reason: to maintain unitarity and causality. Okay? That we are doing quantum mechanics where you start with the initial wave function and you evolve into the future or the final wave function. That's all they're doing, except for symmetry. Symmetry is your choice. You want to have Lorentz symmetry, good for you. If you don't want to have it, that's okay. If you want to have isospin symmetry, okay. That's an add-on. Obviously, all these matrix elements will be as symmetric as the theory you decide to study. Okay? But other than this trivial thing called symmetry, okay, I'm going to call it trivial compared to this, all that's going on here is we're saying that once you have specified the lower order interactions, it's unitarity that's forcing you to all the higher ones. I often phrase this as the question, what would happen, you know? It's like my kids. You say, do something, and they say, what's going to happen if I don't do it, right? What's the worst? Similarly, you can ask me, I don't like to calculate this. I like to calculate this diagram because it's easier. And you say, what's going to happen if I don't calculate this, okay? Surely it just corresponds to a different theory. You know, there's a theory where you add this and this because teacher said so. Or there's a theory where you don't bother to calculate this and you're liberated. Okay? It's easy. And you can say, what would go wrong? How bad would it be? It's still relativistically invariant, right? It's all relativistic propagators and vertices. It's kind of nice. And the answer is, this is what would go wrong. You would not have probability conservation. Okay? That's all that that loop is there for. To maintain that and nothing else. Okay, we're done with this principle, but it comes up again and again. It's an incredibly powerful insight that one uses again and again in different contexts, especially because it's free information. It's in a sense, doesn't matter what type of perturbation expansion I'm doing. And the equation itself is totally not perturbative. And as I said, we are often in a situation where perturbation theory is compromised in some way or another. Infrared divergences or something gets between us and just a robotic application of perturbation theory. Free information, which is non-perturbative, like this, is one of the greatest tools in coming to our aid. So there are all sorts of brilliant results in the strong nuclear force, okay, QCD, where you have truly strong interactions and perturbation theory is not of much use, where all these incredible deductions have been made based on just this equation and causality, okay? And so you get information for free in some way. So we're not seeing a lot of it in this course, but that's why I wanted to do this example so you see how it works. Okay, so we're switching tack now. In some sense, this has been the hard, grungy part of the class, and we're just about to switch to, so let me say two things. One, in a sense, if you have imbibed everything I just said up till now, and played with it a little bit and seen how you got rid of infinities and how unitarity works out, if you just go over this and discuss it with your friends and sort of make it your own, in a sense, you've learned half of what the class is about. By example, not by generality, but by example. We've just done the simplest example of at least half the principles that this course is about. The other half is just gauge theory. Okay, so that's it. That's all I wanted to do in this class as crucial goals. So what's about to happen in this midsection, before we get to gauge theory, is we're just going high-tech. We don't want to do examples anymore. We want to do everything in one shot. So we need to just develop the tools. It's like being a good accountant. You just need to develop accounting tools that allow you to do it. And of course, the more beautiful the accounting tools, the less they put you to sleep. So we are going to hit some beautiful accounting tools. We're going to talk about, again, sources as a kind of accounting tool, not just a way of thinking about thought experiments. And we're going to do path integrals. Okay, so we'll see. We might start path integrals today. Okay, so but this is all in the direction of trying to put your hands around all the amplitudes, whereas you see I'm struggling here. I want to list all of these for you, except there's a continuous infinity number of matrix elements, so I've written down two. Okay, so we don't want to be, in that sense, struggling. The other thing is, this unitarity equation, at the perturbative level, I think it's kind of interesting. It's kind of interesting to see the all-order structure of this equation from the diagrams. It's not a standard part of a quantum field theory class. Usually, at best, one does the examples I've shown you. I usually recommend one thing that you can read yourself, which doesn't take very long, and so it's outside the scope of the class, but it's so much fun to see the way these diagrams work. And that is, so if you can dig it up, it should be on the old website, but that is this article, so for general perturbative diagrammatic unitarity. See this article by, I don't know where the apostrophe goes, with that, on the website as of sometime this week. It should be up. And he shows you how to think diagrammatically about this equation. And the key is not to work in full momentum space. Again, break it into time and spatial momentum separately. And watch the time carefully and see how everything breaks down. And it's a rather beautiful equation that he shows you. It is correct in perturbation theory. The one thing that it misses is sort of the combinatoric factors of perturbation theory. But hopefully, the price you pay for that, I mean, the reward you get for missing that is that you can read it within an hour. Okay, so it doesn't take you days and days. But it'll give you, I think, a deeper insight into how does this magic keep going. We're checking and it's working, but it's sort of a little still, we're in the weeds to see why is it always going to work. And this thing makes it clear, and I think gives you a really good insight. He actually uses this. This article is written in some conference proceedings. It's called Why Do We Need Local Gauge Invariance? Okay, so not exactly this topic. But you can read that part too. You can keep reading it. And it's only a few pages long. But it is really one of the first deep attempts to study the diagrams themselves and see where unitarity is high.
He also has a document called Diagrammer, which is
Yes,
slightly
so there's a
bigger
longer
version.
document. There's a longer document which I might recommend less for a first-time quantum field theorist called Diagrammer. It's not a document. There's a document with him and Veltman, two Nobel Prize winners now, where they try to understand all of field theory from just the diagrams, rather than writing Hamiltonians and this, that, and the other. And so it's interesting, but I somehow think the most interesting part of it is this. There are other things that I just think they wouldn't mean anything to you right now. But this would. This would. This is very nice, simple, and very deep, and it's worth doing it. Just for your own sake. I'm not asking you to. Okay, so we're switching modes. To what we might call functional methods. But what I really mean is high-tech methods that allow us to treat all Feynman diagrams or all of perturbation theory in one shot. Okay? And even maybe get a sense of what non-perturbatively is going on. So we use correlation functions, or Green's functions, or Green functions. We go to the S matrix, and we think this is the thing we can hand off to the experimentalists and so on. And this is some sort of intermediate step, but here they are. They are things that look like this. Again, this is just the interacting vacuum. Not the Fock vacuum, but the interacting vacuum. And so if we merely think of it as some intermediate step with no meaning of its own to go to here, then we should discard it. Of course, it's better and better for your instinct, so that to make every intermediate step something meaningful to you. In a sense, Feynman was very unhappy with the intermediate step of computing the wave function and then squaring it and getting the probability and so on. And so he took his intermediate steps very, very seriously, and the double well thing. Ended up breaking it up into the sum over paths and so on that you know and love. And in the process, developed a lot of instinct for the answer. You could say, look, that's a human aspect of it. I don't need to do it, but we're humans. And so it really does help to attach some physical meaning as much as possible to this object. Okay? And we've been doing it already. by introducing this idea of sources. Okay, so the question is how to think of this as physical. And the answer is to make a time-dependent Hamiltonian in the Schrödinger sense. So let me just repeat this. Let me do it in the context of scalar field theory. So these are all Schrödinger operators. And so we're adding, or if you want, subtracting a source term, okay? And this corresponds, so we've discussed this a few times, but I'm making it official. Here is the region of space-time where J does not equal 0, so it's the support of J. And there's a kind of a new rule, right, which is, if you think of this as a perturbation, it's a perturbation with just one line. As a Feynman vertex, it's just got one line. There's the one line. And you have to integrate over the region where this is non-zero. Integral d cubed x, if it's only a function of, I mean, as far as the Hamiltonian is concerned. When you turn it into a Feynman rule with a time-dependent Hamiltonian, and you work out the Feynman rules, then this thing means you have to, you can take this line, but you have to integrate over where it comes from in the region of J not equal 0. Okay, so I won't go into great detail because I think I've talked to you about this already. But it allows us to talk about something that, again, I've sort of said is the philosophy of start with an empty room, bring out your toys, play with them, and then put everything back